Time for us to do some problems involving arc length, distance, square roots. Oh my. Of course, that means we got to be careful with our algebra. To do that, we practice. The more we practice, the more comfortable we get and the more fun we have. That's why calculus is a lot more fun after you've done it for a couple of years. It's not Stockholm Syndrome. It's not like, we've convinced ourselves it's fun. No, they're actually fun because they become little puzzles once we get over our initial, the algebra phase. And to help us get over that phase, practice. Do as many problems as you can on your own. If you're following along with the video, make use of the pause button. See a good problem to work on? Pause me. And now you try it and see how you do. Whenever you need help, I'm there. You just unpause me and I can come and give you a hand. Well, let's begin. Our first problem. Find the arc length of 2e to the t, a fourth 2t minus 1 e to the 2t, and 2 natural log t, where t goes from 1 to 2. Well, first off, this parametric curve, we're thinking of it as xt, yt, zt as coordinates and points, and we're going to do something really very simple, and that is we're going to do a little doot and doot. Okay, so we've turned it into a vector valued function. Now we can use our tools. So how does it work? Well, we have a basic formula for arc length, and so if we think of these as our x, y, and z, or if we're feeling fancy, z, we can say, hey, arc length is done by the following. Adding up, start to stop, and then we take the square root of the x prime function squared, the y prime of function squared, and the z prime function squared, dt. All right, good. Now we're going to be patient. The vast majority of the work is going to be coming into saying, let's simplify what's inside the square root. And once we've gotten to that, the rest of it will be almost pleasant. Well, hopefully it'll just be pleasant, not just almost. Let's see where we go. Okay, so we start by saying, look, we know where we start and stop, 1 and 2. That's good, so that says we know our bounds, 1 to 2. Square root of, and now we're going to go through each term. Derivative of 2e to the t, that one's easy. 2e to the t. Okay, squared. Plus, okay, well this one we'll use a product rule, right? Because it's a function times a function. So derivative of the first will be 2 times the fourth, which gives us a half e to the 2t plus 1/4 2t, I said 1/4, but I wrote 1/2, 1/4, 2t minus 1, times the derivative of e to the 2t, which is 2e to the 2t. So it's the derivative of the first times the second, plus the first times the derivative of the second. Squared. Don't forget the square. Sometimes you get so wrapped up and like, wow, this is so cool. Then you forgot, oh wait, I got to square this. Okay, now z prime. Well, derivative of 2 log of t, that's not so bad. That's 2 over t squared. Okay, well, the first and the last seem pretty clear what's happening. The middle is a little bit more murky. Let's see if we can't clean that up a little bit before we go too far ahead. So if we expand, so that's 1/2 e to the 2t, and then here, let's see, we'd have 1/4 times 2 times 2. Oh, well, that's just 1. So there will be a t e to the 2t, then 1/4 times minus 1 times 2, and minus 1/2 e to the 2t. And we say, whoa, check it out. We get cancellation. Almost as if somebody intended that to happen. Because I think somebody intended that to happen. It's a good reason why, right? Okay, so what do we have? Well, this is the integral 1 to 2 of the square root 4, all right, t squared is 4, e to the t squared, well, I can say that's e to the 2t. plus, then it'll be t squared, and then e to the 2t squared is e to the 4t, and then there's a 4 over t squared. All right, great, good. Now we said, okay, that's what our x prime squared plus y prime squared plus z prime squared becomes. The next thing we got to do is start thinking, is there a way to simplify? Well, there's not really much in common. In fact, I don't think there's anything in common. Okay, but there is 3 terms. Now you might say, well, what does that do? Well, when I see 3 terms, I start to think, oh, a squared, 2ab, and b squared. Now, what could we have? Well, let's see if it works, right? So if we think of this as a squared, 2ab, and b squared, well, if this is our a squared, that would be 2e to the t squared. B squared would be 2 over t squared. And if you multiply these together, you end up with 2ab would be 8e to the t over t. Wait, that's not what we have there. Darn it. I was really hoping it was going to be a square, though. Oh, wait a second. Hold on. I think they're messing with us. Okay. It could be a square, but it doesn't have to be the case that they gave it to us in the right order. In other words, a squared, 2ab, b squared. Maybe it's jumbled up. Okay. All right. So let's think about it. Let's not try to guess. Let's try to be a little bit more methodical and see if we can figure out, well, which part should be the squares, which part should be the middle. So we can write every one of these as a square because they all came from squares, right? So this one would be 2e to the t squared. This one would be 2 over t squared. This one would be te to the 2t squared. Now, well, what do we want? What do we want? We want to find some right combination where it all works out beautifully. And in other words, what? Well, I'd like to have, okay, so here's sort of the idea. I'm thinking it's a quadratic, so I should have an a squared, a b squared, and a 2ab. So what I should check is I should say, well, let me see if it works. So I can pick which one should be the a squared and the b squared. So the way we check is to say, well, what about the other term? Is it 2ab? See, if we started here, we saw the middle term doesn't match. So that's not going to work. Well, what if this were the a and the b? So then what we would get is if we multiply these together, we would get 2te to the 3t. Now that does not match 4 over t squared. What if this were a and b? Well, what would we have? Well, we'd have the t's would cancel, and we get a 2e to the 2t. But remember, there's an extra 2 in there, 2ab. That does match. Aha! It is a perfect square. We just have to do some rearranging. Okay, so this is, we're going to rearrange. Integral 1 to 2. We'll move this first term, this t squared e to the 4t. We're going to move this to the front. We're going to move that to the middle. So we have really t e to the 2t squared. And then this 4e to the 2t, how are we going to think of it? Well, we're really going to think about it as 2 times te to the 2t times 2 over t. And then the last term will be a 2 over t squared. In other words, we saw if this was the a squared, this was the b squared, this was 2ab. So a squared, 2ab, b squared. And now we're in great shape. We've got ourselves a nice square. So this becomes the integral 1 to 2 of the square root of te to the 2t plus 2 over t squared dt. Okay, which means we can get rid of the square root. Now notice There's absolutely no problem with things being negative, so we don't have to worry about, do we have absolute values? No. No concerns here. So that gets us to this point. We need to integrate from 1 to 2 of t e to the 2t plus 2 over t dt. Okay, now, how do we integrate? Now you're probably thinking, we're going to have to pull out our integration by parts, and we're going to take a few minutes here, because it's taken us, it's been like a year since we've done integration by parts. Or we could say, you know what? If I'm looking for the antiderivative of t e to the 2t, I just need to find something whose derivative was t e to the 2t. Have we seen any function in the last couple of minutes whose derivative is t e to the 2t? Any function at all where when we took the derivative we got t e to the 2t? Anything pop out? Anything? Yeah, it's the y. The y of t, when we took that derivative, came out to t e to 2t. So when we take its antiderivative, we can just put it back in. So this becomes, the integral of t e to 2t is that. So 1/4 2t minus 1 e to the 2t. Okay, that's the first piece. Plus the integral of 2 over t, we could say, same trick. 2 over t we also know. We can do that. That's 2 natural log t. And we're going to evaluate from 1 to 2. So the last thing for us to do is to evaluate, and then we're done. Okay, so let's plug in 2. So what do we have? 4 minus 1 is 3 times a fourth. So we end up with 3/4, and then it'll be e to the 2 times 2. So 3/4 e to the 4th. All right, good. Progress. Now, plus 2 log 2. All right, 2 log 2. Plug in 1. And we're going to subtract 1/4. Then here, 2 minus 1. 2 minus 1 is just 1. So it's going to subtract 1/4 e to the power 2. Okay, that's good. Cool. And then 2 log 1. And that's going to be subtracted. But 2 log of 1 is 0. Log of 1 is 0. So we say, that's the answer. And we're done. We're done. It worked out rather nicely in our case. Well, oftentimes they do, right? We take our derivatives, we're careful with our algebras. When we see 3 terms, we say, hey, that's probably going to be a perfect square. And so we start to predict, okay, if it's a perfect square, which parts are the a and the b, which parts the 2ab. We might have to play around with it. It may not necessarily be exactly in the order they've given it to us, but that's okay. We're adaptable. We can adapt. And there we go. Good. Great. Well, let's keep going. We're going to do some more problems, right? Of course we will, because we know the more that we do, the better we get. So, find the length a particle travels along the curve. R of t is t squared sine ti minus t squared cosine tj plus t squared minus 17k for the time interval where t goes from 1 to root 8. Now, we see keywords. We see length, so we know that we're dealing with a length problem, or in other words, a distance problem. Then you might say, well, of course we're dealing with a distance problem. That's our session. But keep in mind, in the future, you might not be in a session. You might be seeing a problem out somewhere in the wild and be like, whoa, what's that problem over there? It's good to learn to recognize patterns. Okay, so we know it's a length problem. Notice that they gave our function to us in a slightly different way. Instead of component form, where it's like, you have your bracket, thing, bracket, it's like something times I plus something times j plus something times k. Perfectly fine. They can give it to us in many, many different ways. So be ready to adapt. In other words, be flexible. Now, if you prefer to work with I, j, and k, then keep working with I, j, and k. I like working with components just because it helps me keep track of things. So one of the things I'm going to do here at the start is I'm going to put things into components. So I'm going to say, look, another way I could have written this function is as t squared sine of t, comma, minus t squared cosine t, comma, and t squared minus 17. All right, so there we go. Now, to begin, let's take r prime. So what is r prime? Well, product rule. Derivative of the first. Well, derivative of t squared, 2t, times the second, sine t, plus the first, t squared, times the root of the second, cosine t, comma. Then we have the derivative of the first, minus 2t, times the second, cosine t. And then the first, minus t squared, times the root of the second, derivative of cosine, negative sine. So that makes it a plus. Okay. And derivative of t squared minus 17, 2t. Minus 17 really doesn't do anything. It's a shift. It's in particular what it is, because it's in the z component, it says shift everything down. It doesn't change your length when you shift your length. So no surprise, it goes away. Now, in essence, what we really need to do to find the length of the particle is to get a handle on speed. And to get a handle on speed, well, we want to figure out the magnitude of r prime. So that's going to be the next thing we do. The magnitude of r prime of t. And if we do this is probably like 80%, maybe even more of the problem. It's just saying, let's clean this piece up as much as we can. As much as we can. And if we can get it really clean, the rest of it will just flow naturally. So we're going to be very patient here. We're going to have a square root of, well, we have the first term, 2 sine t plus t squared cosine t squared. And then we're going to have the second term, minus 2t cosine t plus t squared sine t squared. Okay. And then plus 2t squared. All right, so that's a lot. Well, now we're going to be patient. So this is the square root of. When we square this term out, we're going to have what? Well, we're going to get 4t squared sine squared t. Then we have the cross terms. Don't forget that. So a squared, then there's 2ab. So the 2ab will be what? Well, it'll become 4t cubed sine t cosine t. And the last term squared, t to the fourth, t to the fourth cosine squared t. Okay, so there we go. That's the first piece squared. Now the second piece squared. Okay, so it'll be, I'm running out of space, so I'm going to go underneath it. Still the same piece, 4t squared cosine squared t. The cross terms, well, there will be a minus because there's a single minus. 2ab, so there's 2 times 2 makes a 4. T times t squared is t cubed. And cosine t sine t plus t to the fourth sine squared t and plus another 4t squared. Okay. Now, if we've lived a good, clean algebra life, some beautiful things should happen. I think we have lived a good, clean algebra life because I suspect some wonderful, beautiful things are about to occur. I see these terms, the 4t cubed sine cosine, 4t cubed cosine sine. They're opposite, so they cancel. They're gone. Beautiful. But it doesn't stop there. Look at here, the 4t squared, and then there's sine squared, and there's a cosine squared. So when you put them together, you end up with a 4t squared. Similar, on the end, t to the fourth times cosine squared and sine squared. When you put those together, you get t to the fourth. And so, well, what do we have? We have a 4t squared a t to the fourth, and another 4t squared. So if we put that all together, we get the square root of 8t squared plus t to the fourth. Okay, that's fine. We can do something here. They have something in common, t squared. Let's go ahead and pull it out. Now, what's the square root of t squared? Well, you should be careful. And so I'm going to be a little bit careful here, just because, well, I've been burned before, right? So what happens? The square root of t squared, technically it's the absolute value of t. Because when you square something, you lose the sign. When you take the square root, you always end up with the positive aspect. But notice our t here is from 1 to root 8. So we don't need to worry about absolute value. So for our specific range of t, we can say, aha, it becomes t square root of 8 plus t squared. And now we're ready to go. We've done the hard part of the problem. The rest of it is just the fun part. Well, what do we mean by that? Well, let's get into the rest of it. You see, our length is you add up from start to finish, so 1 to root 8 of your magnitude of r prime. So magnitude of r prime is t square root 8 plus t squared dt. Okay, now how to integrate this? Well, the way we do it is make an observation. Say, look, this looks like a function in a function, and in this case, if you set u equal the inside piece, 8 plus t squared, then du would become 2t dt. We say, if only there were a 2 there. Okay, let's put 1 there. And then you're like, whoa, you just can't put 2's anywhere you want. Well, I almost can. I just have to make sure if I do put a 2, it balances out with something. So in this case, we'll multiply by half. See, the half and the 2, it's the same as multiplying by 1. Perfectly okay. You are definitely allowed to multiply by 1. So what do we have? This becomes 1/2 integral the 2t dt du, the square root of 8 plus t squared, square root of u, which in calculus we like to write as u to the 1/2, and the bounds. If if t equals 1, u would be 8 plus 1 squared. Well, that makes it 9. If t equals square root of 8, 8 plus square root of 8 squared, that's 8 plus 8, which makes it 16. Now, we should feel pretty good about ourselves right now because we see and say, wow, there's something involving a square root, and our bounds aren't just random numbers. 9, 16, these are beautiful numbers because they're squares. That means we're probably on the right track. Oh, this is good. Okay, so now we integrate. So this would be 1/2. Integral of u to the 1/2 will u to the 3/2 multiplied by the reciprocal, 2/3, and evaluate from 9 to 16. So 1/2 times 2/3, the 2's cancel. So we have 1/3. Then we're going to have 16 to the 3/2, and then we're going to subtract 9 to the 3/2. Now we start thinking, okay, 16 cubed. Well, of course, we all know 16 cubed is 4,096. That's just common knowledge. And the square root of 4,096, well, of course, that's 64. And you're probably thinking, I don't know if it's common knowledge, Steve. But of course, we're doing it the wrong way, right? So if we're doing 16 to the 3/2, start with the square root first. Square root of 16 is 4, and we have to do 4 cubed. So let's see, 4, 16, 64. Okay, so that's 64. And 9 to the 3/2, okay, 9 cubed, yeah, come on, give me a break. What are we really doing? We're really taking the square root of 9, which is 2, square root of 9, which is 3, 9 to the 1/2, 3, and cubing it. 3 times 9 times 3 is 27. Okay, so subtract 27. All right, well, if you take 64 and you subtract 27, that's a number. we can be a little bit more precise. It's 37. So we end up with 37 over 3. And that's the answer. And it worked out surprisingly nice. Beautiful, actually. It's one of the things that happen when we often have like these sines and cosines. If they're multiplying by the same function in front, don't worry about the plus or minus. When you expand, you'll get this type of behavior where the middle terms will cancel and you'll get some cosine squared and sine squared. And as a consequence, it just simplifies beautifully. So oftentimes it looks like it's going to be bad, but if you're patient with your algebra, and a little trick, I know, thrown in on the side, it becomes clean and elegant. All right, well, what a fun problem. Good stuff. Good times. And to keep the good times going, let's do another problem. Find the distance traveled along the curve, 1/5 t to the 5th minus 1/2 t to the 4th plus 1, square root of 5/4 t to the 4th plus 3, 4/9 t to 9/2 plus 7, where time goes from 0 to 4. All right, well, how bad could it be? I don't know. We haven't done it yet. We'll find out, right? Okay, so what do? Well, it seems like it's fairly straightforward. Of course, we'll say, look, think of it as really vector valued function. So you have your x, your y, and your z. And nothing seems particularly bad. So let's begin. So what do we see here? We have the length is the integral, start to stop, of the square root of x prime squared plus y prime squared plus z prime squared dt. So that's just a generic formula for length. So in our case, start and stop, 0 to 4. All right, no surprises there. Square root of, all right, take the derivative. Well, the derivative of 1/5 t to the 5th is t to the 4th. The 5 comes down and cancels with the 1/5. Derivative of 1/2 t to the 4th would be minus 2 t cubed, because the 4 comes down, 4 times 1/2 is 2, and the plus 1 goes away. All right, squared plus, okay, here, derivative of t to the 4th, well, the 4 comes down, and so we really end up with a square root of 5 t cubed squared. Wow, there's some big terms in here. All right, and here, well, 4/9, the 9/2 comes down. 4/9 times 9/2. We maybe should write that one down. That might not be the easiest to do in our heads. And then it'll be t to the 7/2 squared. Okay. So the 9s, okay, they cancel. 2 goes into 4, so it leaves us with a 2. All right. Not so bad. So let's see what we have. We get integral 0 to 4, the square root of, square this out. So t to the 4th times t to the 4th would be t to the 8th, right? T to the 4th squared, right? Is t to the 4 times 2. All right, it's not t to the 16th. That's wrong. We'd be in trouble. No, it's t to the 8th. Okay, our cross terms, that would be minus 2ab. So in our case, minus 4 because of that 2 times 2. T to the 4th times t cubed. You add the powers, t to the 7th. Square the last term, that would be 4t to the 6th. Here, what do we have? Well, we have square root of 5, and we square that, that's 5. T cubed squared, t to the 6th. Oh, that's kind of nice. And here, 2 squared is 4, and then t to the 7/2 squared is t to the 7th. Okay, well, what's going on here? Well, we see, okay, that 4t to the 7th, cancel. Great, beautiful. All right, and and these combine. Okay, so that's like 9t to the 6th. Well, what happens next? Looking at it, we have two terms, t to the 8th and t to the 6th. Let's factor out the common stuff, because that's oftentimes a good strategy. So if we did that, we'd have integral 0 to 4, and we'll go ahead and do it in a couple steps. So I'm going to pull out a t to the 6, and then we have a t squared minus 9. Okay. Oh, plus 9, not minus 9, because 4 and 5 are both positive. Okay. Now, the square root of t6 becomes t cubed. If you've been watching, you might say, whoa, what about, do I need to worry about absolute value? And the answer is no, because where t is positive. You probably think, man, why do you make me so paranoid about absolute value? Well, the one time that we're not paranoid about it is the one time it's going to matter. So we just want to get into the habit. I don't want to say we're paranoid. We're just methodical. The one time we forget to check is the one time we'll wish we had checked. Okay, great. We're making wonderful progress. This is feeling great. Well, now what? How do we go forward? Well, I think we've done stuff like this before, right? We say, okay, let's just, we have this inside function, t squared plus 9 inside the square root. That seems like a very strong candidate for substitution. So we'll say, hey, let's let u equal t squared plus 9. And then we can say du is 2 times t times dt. Now, this 2, we could put a 2 there and a half there, or another way we can do it is we can actually just write this as a half du is t dt. And at this point, you're like, oh, we were so close. Oh, but what's happened here? That pesky t cubed. If it had just been a t, we would be okay. In fact, we would be happy. But it's a t cubed. There's 3 of them. We only won 1 of them. Why? Oh, what can we do, though? Well, true story. One thing we can do is say, t cubed is actually t squared times t. It's true, totally true. You can check it out yourself. Okay, now you might be thinking, that's fine. I can handle a 1t with the t dt, and that gets me du. But I want those other t's, the t squared. Because remember, whenever we do a substitution, everything has to change. So if I see a t squared here, it's got to transform to something involving u. Is that possible? And how? Well, note, we can say something about t squared and u. U is t squared plus 9. We could have also said, hey, t squared is u minus 9. So I can replace the t squared in terms of u. That says I've got all my bases covered. I can change that t squared. It's u minus 9. That t with the dt becomes the du. The square root of t squared plus 9 becomes square root of u. I'm good to go. So this is a fantastic substitution to make. Indeed, it's just the right one. Just right. It balances out all the pieces that we need. So what do we have? After our substitution, this becomes the integral. So the t squared, u minus 9, the square root of t squared plus 9, square root of u, which we're going to write as u to the half. The extra t times dt becomes a du times a half. So we'll put the half out here in front. Are we done? No, because we've got to do the bounds. Always remember, you have to update the bounds. We started with t bounds. We want to get to u bounds. So we say, okay, our bounds here are from 0 to 4. What do they become here? Well, to figure it out, you plug in. This is t equals 0. So you plug in t equals 0. U is 0 plus 9. So our lower bound is 9. Oh, that's kind of nice. It's a perfect square. 4. Okay, that's t equals 4. Plug in t equals 4. 4 squared, and 7 years ago, wait, no, that's something else. 4 squared is 16, plus 9 is 25. So our upper bound is 25. And now, that's another nice number, another perfect square, almost as if it had been planned, because it was planned. Yes, I hope one of the things that you start to appreciate, these aren't just random. These are the pearls, the most beautiful ones that we can come up with. Okay, so we're going to go from 9 to 25. I pull out the 1/2. Now what do we do? Well, we can distribute. So we're not ready to integrate yet, but we can distribute this u to the 1/2 through. So it becomes u to the 3/2 minus 9u to the 1/2 du. All right. Well, everything's ready to go. So we proceed. We have a 1/2. So integral of u to the 3/2. Well, add 1, that'll become to the exponent 5/2, multiply in front by 2/5. Then here, minus 9, add 1 to the exponent, u to the 3/2, multiply in front by 2/3. And we're going from 9 up to 25. Okay, all right. We're still barely on the edge. Okay, but we're still there. All right. Well, we can clean it up a little bit. What does this become? If you multiply the half through, we end up with, let's partition this off so we can follow where we're going. A half times 2/5 is 1/5 u to the 5/2. And then a half, and cancel with that 2, a 3 cancels with that 9, at least a little bit. So minus 3u to the 3/2 from 9 up to 25. Okay, well, let's plug these in and see what we get. So let's plug in 25. Okay, well, this will be interesting. So what do we have? We have 1/5 25 to the 5/2 minus 3 times 25 to the 3/2. And then we're going to subtract 1/5 times 9 to the 5/2 and subtract 3 times 9 to the 3/2. Okay. At this point, if you wanted to stop, I wouldn't blame you, and we probably could stop here. But I'm just going to poke it just a little bit more because I like to live dangerously. Let's think about what's happening here with the first term. We have 25, and then we're taking a square root, which gives us 5, and we're taking 5 and multiplying out 5 times. Now, 5 to the 5th is 3,125, as we all know. But actually, we're not going to do 5 to the 5th because that says we have 5 5s upstairs. We have 1 5 downstairs. So we'll cancel a 5. One of the 5s from upstairs with the 5 downstairs. So really just doing 5 to the 4th. And that's 5, 25, 125, 625. So this is 625. Okay, that's good. So 625. And then we have 25 to the 3/2. Well, 25 to the 3/2, again, that's square root of 25 is 5. Multiply that out 3 times. 5, 25, 125. 125 times 3 would be 375. Okay, so that's the first term. Subtract. Okay, 9 to the 5/2. Square root of 9 is 3. 3 to the 5th, 3, 9, 27, 81, 243. So that's 243 fifths. And then we have minus 3 times 9 to the 3/2. Well, square root of 9 is 3. 3 cubed is 27 times another 3 makes 81. It's all there. Like I said, if you were like, I should have stopped, it's okay. You could have stopped. 625 minus 375. Well, that's 250. That's it. That's the difference between the two. So this first term here, there's a 250. Now minus minus makes a plus 81. Then subtract 243 over 5. 250 plus 81, 331. Yes? So that's 331 minus 243 over 5. Now, if we were to go all the way, 331 times 5. Well, that would be 1,655. So you get 1,655 fifths minus 243 fifths, and that will leave us with something over 5. Well, what's the something? Okay, well, it's not so hard. 5 subtract 3 is 2. 5 subtract 4 is 1. 6 subtract 2 is 4. So we end up with 1,412 fifths. So 1,412 fifths. Wow, cool. It worked out to a number. But probably you could have left it here. Or maybe even use a calculator. What? Yeah, you probably could have used a calculator. All right, what a problem. What a great problem. Well, let's finish up with one more wonderful problem. So our last one. You find yourself setting off on an adventure that takes you from a small village on a steep trail through the mountains. Ooh, this sounds great. I've always wanted to have a nice application for calculus. So apparently adventuring, that's good. All right, so wait, how does it continue? You casually notice that the trail on which you will travel could be described by the parametric curve. Okay, so we got 4t, 8/3 t to 3/2, and t squared. I like how we do it all casually. Wow, this must be after we've gotten really comfortable with doing calculus. But okay, all coordinates are measured in furlongs. That's an old-timey measurement of distance. And the village is located at time 0 and moving in the positive t direction. Okay, so what should we be thinking of here? Well, we have, there's some sort of mountains here. Who knows? And then down here, we have the village. Okay, so here's our village where we start off, and we're going to be going through the mountains. So we're moving up through the mountains following this path. All right, now picking up again. After you have traveled a total distance of 21 furlongs on the trail, you see that you must quickly send a message back to the village. You have a falcon with you that has been trained to carry messages directly from wherever the current location is back to the village. How many furlongs must the falcon fly to return to the village? This is so cool. What? Okay, we got to think about what's just happened here. So we've moved. Now the trail isn't a straight trail. It's not a line. If it was a line, it'd be like something t, something t, something t. But, that means in different coordinates, we're traveling at different speeds. So it's somehow twisting. It's this twisting curve. So what do we know? Well, we know how far we've traveled so far. We know we've traveled 21. We don't need to worry about units. Since everything has been measured in furlongs, then everything works out. We can ignore units. So, but that's not traveling in a straight line. Our wonderful falcon is going to go directly back. Now, directly means straight line. So the falcon is going to say, aha, I'm not forced to go on a road or on a trail. I'll just fly directly in three-dimensional space. So the falcon is just going to say, hey, I'm going straight back. So what do we need to find? Well, what we need to figure out is what's the distance from where we started to where we're currently at. Which means we need to know where we're currently at. Okay, so there's a lot of steps here, and we have to sort of unwrap this. By the way, let's just point out at time 0, we're at 0, 0, 0. So we really are just trying to figure it out. The question is, how far are we from where we started, given that we've traveled 21? Okay, so let's think about it. Now, what's the right tool? What's the key word? If we saw this problem out in the wild, we said, what's our tool that we need? Is there any key word or key phrase to help us out? I think there is. This part right here, total distance. So I would say, this is a distance problem here. Okay, I can see that. So we're trying to figure out, all right, how far have we traveled? Well, we actually know the exact answer. We know our distance is 21. So we say, okay, normally we say our length is adding up from A to B, the square root of, and it's x prime squared plus y prime squared plus z prime squared dt. But we know our length, that's 21. We know where we started at the village. So we started at 0. What we don't know is where we stopped. So we don't know what b needs to have as the value. Okay, square root of, well, x prime squared, that'd be 4 squared. All right, how about y prime? 8/3 t to the 3 halves. Okay, 8/3 t to the 3 halves. The 3 halves comes down, right? So, well, okay, let's just be careful. 8/3, 3 halves comes down, t to the 1/2 squared, and then 2t squared. Okay, so let's see, what do we have here? That's the integral of 0 to b, the square root of, well, we have 16. Here the 3's cancel, and then we have 8 divided by 2 is 4, so it'll actually be another 16t, and then here we have 4t squared. Okay, well, all of these have 4 in common. Let's pull it out. Now, the square root of 4, by the way, also known by another name, 2. So this becomes 2 square root. And if we reverse the order, t squared plus 4t plus 4. Well, what would be nice? It would be really nice if what was inside was a perfect square. And it's really nice. It is a perfect square. Life is good. Do you see what it is? It's t plus 2 quantity squared. So we can take the square root very simply, very beautiful square root. So it becomes, and we don't need to worry about absolute value, everything here is positive. T is greater than or equal to 0. So 2 times t plus 2, which really becomes integral from 0 to b of 2t plus 4. Say, great. Well, that's t squared plus 4t. And we need to evaluate from 0 up to b, which becomes b squared plus 4b. Now, what do we have? Well, we have, if we work our way back, that equals 21. Okay, all right. So we say, great, b squared plus 4b minus 21 has to equal 0. So we need two numbers that multiply together to give 21. There aren't that many. There's 1 and 21. That's not going to give us anywhere close to what we need. 3 and 7. Okay, so 3 and 7 has to be it, because they have to multiply together to give 21. And when we take their difference, we have to get 4. So we need a plus 7 and a minus 3, right? Because that's b squared. 7b minus 3b is 4b, and minus 21. So that gives us two possibilities, b equals 3 and b equals negative 7. Now, we can throw one of them out. We were told, where? Look, we start at time equals 0 and moving in the positive t direction. In other words, time is positive. So what can we throw out? We can throw out the negative. That's not possible. And you're like, cool, our answer is 3 and we're done, right? No, our answer is not 3. Okay, wait, what? Okay, so what have we figured out? Well, what we figured out is that we know where this point occurs. We don't know what the point is, but we know for which value of t it occurs. And in particular, we say, aha, this point out here corresponds to t equals 3. Now that we know the value for t, now we can say, well, what's the point? Well, so we plug it in. So the x value, 4 times 3 is 12, comma, the y value, 8/3 times 3 to the 3/2. And the z value, 3 squared, 9. So that is, after we've traveled the distance of 21 furlongs, that's our location. That's where we're at. Okay, so that is where we release our falcon. Okay, our falcon is released. It goes back to the origin. So to finish the problem, the distance that the falcon travels is the distance from this point to that point. So that's what we need to find. Well, because this is 0, 0, 0, that's not so bad. It's not so bad at all. So finally, we say, look, our distance will equal the square root of the change in x. Well, that'll be 12 squared. Change in y. Now we can, by the way, before we get too far ahead, 3 to the 3/2. If you think about it, it's like there's 3 copies of root 3. If you put 2 copies of root 3 together, that's a 3. So this piece right here is the same as 8 times square root of 3. So plus 8 square root of 3 squared, okay? X value squared plus y value squared plus the z value squared. All right, so that's the square root 144. All right, 8 root 3 squared. Well, that's 64 times 3. Because 8 squared is 64, square root of 3 squared is 3. 64 times 3 is 192. 9 squared, 81. Okay, all right, I'm going to do some little adding here. 4 plus 2 plus 1, that's a 7. 4 plus 9 plus 8, that's a 1, carry a 2, and that would be a 4. Okay, so it looks to be the square root of 417. And that doesn't simplify any. So that's our final answer, the square root of 417 furlongs. All right, that's the answer. Wow. Beautiful problem, beautiful problem. What a nice one to answer it on. I'm going to show you, look, calculus has applications everywhere. You might just be an adventurer setting off on a medieval type world. Well, it's good to know calculus if you want to do these things, because who knows? Otherwise, you might not know exactly how many furlongs your falcon would fly. Could you imagine living in such a world that you wouldn't be able to figure that out? Ah, it would be so sad. But, all right, good. We have our tools. We were able to do fun problems, and so we'll keep going. And keep working on it. Keep doing the practice. The more you practice, the more fun these become. These become puzzles. They're not hard problems you have to sort through. They're fun problems like, ooh, let's see if we can figure it out. So keep at it. And I'll see you again in another session. Hey guys, it occurred to me that I should have pointed out that there's kind of a nice sort of check to see if your answer is reasonable. Now, square root of 417 is not a nice number, but you know, you can use a calculator and we can note, look, square root of 417 is approximately 20.4, which says what? Well, it's about 20.4 furlongs that our falcon has to fly. Now, what's our check? Well, our check is whatever distance the falcon has to fly, it better be less than the distance we've traveled. Because if somehow the falcon had to fly a longer distance, that means that we've made a terrible mistake, because it can't be the case that the straight line distance is longer than our sort of roundabout way. So this is sort of a nice confirmation that it's possible that we did things right. Well, of course it's more than possible. We were careful. You might say, wait a second, we traveled 21, the falcon is going 20.4. That's not a huge savings. Well, not this time, but who knows? That says our route was not too windy. It just wound a little bit. But in the future, if you kept going, it may have been even better savings in the long run. I just want to point that out, though, that, when you have a problem, ask yourself the question, is my answer reasonable? And if it's not, whoops, okay, go back and check your work, because, one thing we can say about math, we're very reasonable. All right, take care.